Again, this is out of Lawrence Berkeley National Lab and was published in the Physical Review, Accelerators and Beams. So what is the top line on this paper?
Yeah, the basic idea is in order to make muons, usually you need like extremely large particle accelerators. Okay. And these guys have done it in effectively the size of like a lab, maybe a big lab, but it's still not like, the size of CERN or like SLAC, where it's like, hundreds and hundreds of meters worth of stuff to create a muon beam. And that becomes really, really relevant if you're trying to use muons to do CAT scans on very large things. For example, the pyramids or a volcano. And so that's sort of the stuff we're going to get into.
Got it. Okay.
Okay. But to prime this understanding, we need to first understand what is a muon. Okay. So a muon is a central part of the standard model of particle physics. It is one of the fundamental particles that is kind of like a heavy cousin to the electron. Okay. A heavy cousin. Now, one of the mysteries of particle physics is that particles come in 3 generations. Okay. There's the electron, which is a class of leptons, and then there's this thing called a muon, and then the tau. You might have heard. You're smiling because
it just makes me think of Pokemon.
yeah. But well, it's exactly that, and actually, it's one of the big mysteries that is still unsolved today. Okay. Why it comes in these 3 generations. But in any case, that's the universe that we live in. This muon is exactly like the electron, except it's 200 times as massive as the electron. So here we've got a photo of the particle, all of the particles that make up the standard model. This is everything that we are made out of. Not just the mass, but also all of the energy that we're made out of. The light, the photons are part of the standard model. The stuff that is massive, like the up and down quarks, those are the stuff that make protons and neutrons. The electron together makes atoms. So all of these things are fundamental to our universe. Mm-hmm. And yet, what we're most familiar with is up and down quarks and electrons, right? Those are the stuff that make atoms. And then photons and obviously stuff like that. But in terms of stuff that have mass, muons are this elusive kind of particle. They're quite rare. And they're rare because they're really unstable. They have a mean lifetime of about 2.2 microseconds compared to an electron, which is extremely stable, right? And they were first observed in these things called cosmic ray showers, which are these showers that come when a cosmic ray hits the Earth's atmosphere. A cosmic ray is a really highly energetic, massive particle. Maybe it's like a giant atomic nucleus. Obviously, that's small, but in terms of like particles, it's quite big. When these things come from wherever, galaxies, supernovae, whatever, and they come and they hit our Earth's atmosphere from high up, they release a shower of particles because they interact with a bunch of particles in the Earth's atmosphere. And part of that shower goes from kaons and pions. Those things then disintegrate into muons. And then that's what we usually see. That's where we usually see muons.
Is this related to when folks have the charts of the sun having these large solar bursts and then it reaches Earth's atmosphere and everyone's like, that's what's going to kill the grid? Is that a similar concept as these cosmic rays, or it's a different?
It's similar in the sense that it's a massive gust of charged particles from our sun that is so massive in flux that it starts messing with our electrical grid. Cosmic rays, on the other hand, are very, very sporadic. They're rare. They come from all over the cosmos, so they're not like pointed from one direction.
Yes.
When the sun releases a flare, all of those charged particles come all at the same time, and then they completely overwhelm the electrical environment of the Earth.
That makes
right?
sense.
With cosmic rays, they're once upon a time they come in, and then they have these showers, right? And what you can do is you can have detectors all over the Earth that catch the particles that come in, and then based on the geographic layout of all of the detectors and the timing of when each detector went off, you can be like, oh, it came from that direction, right? Because if it came from that direction, then that detector would go off first, the one that's closest to that angle, and then the one that's further would go further. So it's sort of a way that we've used, muons are a way that we've used to map out cosmic rays, right? And they've been coming at us for forever. Okay, they're ubiquitous, they're harmless. The flux is really weak. It's about 1 a minute through your fingernail.
Okay.
Okay. Like right now, as we're sitting here, there's about 1 muon a minute coming through our fingernail. These things don't really interact all that much because they're so heavy. They'll just like go right through, right? So historically, it's just been like something that's been nice to know about the universe, that we've got this particle, right? That's the second generation.
It's sort of, it's not pop music. It's niche underground. When you're digging in the crates, it's cool.
Yeah, it's cool. And it's got some really cool like implications in fundamental physics research. Like for example, you can make a hydrogen atom, but instead of an electron, you can stick a muon around it, because the muon also has a negative charge, right? And so, but the muon is 200 times more massive.
Right.
So what that means is the size of that muonic hydrogen atom is going to be way, way smaller, which means you can now start probing effects of the nucleus. Like you can start asking questions like, how big is the proton? Right? With a normal hydrogen atom, the electron cloud is so big that the size of the proton doesn't really matter. But if you start shrinking the size of the hydrogen atom, this is one of the ways that in fundamental physics, people start trying to figure out what is the size of the proton. They use muonic hydrogen. So it's like, it's the twin of the electron, but it's just like big.
Makes sense.
That seems to be the only thing that is different about it.
It's big bro.
Yeah, exactly. And you know, it's been a nice quirk up until the 1960s, okay? In the 1960s, there was a guy, Luis Alvarez. He was a Nobel laureate. He was actually played by Alex Wolff in the Oppenheimer movie.
Right.
Right. Who's a very famous actor. Luis Alvarez, in the Oppenheimer movie, he was a PhD student of Lawrence, who was making the first cyclotron in Berkeley. And Alvarez was the guy who read the discovery of nuclear fission, and he replicated the experiment, and he was all excited. Well, when he got older, he started. He was a great experimental physicist. Okay, and he started realizing that what you could do is you could use a muon the same way that we use X-rays in medical imaging. Okay, the principle of X-rays in medical imaging is you have an X-ray source, you have a detector on the back, right, and then the X-ray is going to penetrate through soft tissue because there's not a lot of stuff that's like there. But the denser stuff, like your bone, it's not going to be able to penetrate, and that's going to create a shadow. So then you can image an entire skeleton
on the
using
detector.
X-rays, right? Now, the same principle we can use now for very, very large things, because the muon is kind of like an X-ray in that the path that it takes, how far it gets through something, is dependent on the density of the stuff that it's going through. Okay, fundamentally, it's most of particle physics is that. Okay, it's like, so it's going through, and because it's this massive cousin to the electron, it doesn't actually interact that much with matter, and so it can go through a lot more stuff before it gets stopped. Okay, so now you can start imaging things like buildings or volcanoes, or in the case of Luis Alvarez, in the 1960s, he imaged the Pyramid of Khafre in Giza, which is the second pyramid. Okay, there's 3 big pyramids in Giza. The second pyramid, the one that still has its cap on, that's the one that he imaged. He actually took a muon detector to the inside of that pyramid, put it there for like about 2 years, and you know, the flux, again, as I was saying, from these cosmic rays are really, really small. So you got to wait a really long time to get a nice statistical signal to be like, is there, and the question he was trying to answer was, is there a cavity inside the Pyramid of Khafre? Okay, is there like a hidden chamber? We're always worried about
all the secrets.
Yeah, all the secrets, right? We're always worried about hidden chambers. It was a negative result, actually, because he didn't find any hidden chambers in the Pyramid of Khafre.
This is interesting. This was happening in the 60s.
In the 60s, yes.
This is quite some time ago.
Yeah.
And I imagine Luis Alvarez, if he saw what they're doing at the pyramids now, I don't know if you get these videos on TikTok of DJs with these massive light shows in front of the pyramids of Giza.
I've seen those.
It looks like they're mapping muons with the amount of just, you know, lasers that are going. I obviously that's not what's going on.
No, it's like visualizing his experiments somehow.
Right.
It's pretty cool.
Anyway.
Yeah. So he didn't find anything, right?
Right.
But that sort of started this idea of we can actually do something with muons and do a kind of muon tomography. It's kind of like a CAT scan, where what you can do is take a scan with muons in this direction, and then a scan with muons in this direction, in all these different directions, map out the shadows, and then from that reconstruct the physical 3D nature of whatever is inside.
So this was sort of this understanding that we can use, muon detectors as a means by which to do mapping of large objects or spaces.
Yes, large objects, right? And actually, in modern times, there's been a renaissance. There's been this program called the Scan Pyramids. In 2015, they actually used it to map out the Great Pyramid of Giza, which is the Pyramid of Khufu, I believe. That's the biggest of the three. And they actually did find a void there. They found a previously unknown void. It was at least 30 meters long above the Grand Gallery. And there you see the muons are coming in from cosmic rays. And you're basically waiting for these muons to come in. And from each direction, you can map out how many muons came in from each direction. And you can say, oh, actually more muons came in from this middle part of the pyramid than from the outside, which means that middle part of the pyramid must have some kind of cavity or hole where the muons had no problem getting through. Does that make sense?
It does.
So it's like there's a hole.
Yes.
There's a hole in there. And they actually found it. But it highlighted a limitation of the approach.
Okay.
Which is that you got to wait months to years to actually scan this stuff. Because the flux from the cosmic rays is so low. Okay? Now, this has applications elsewhere as well. Okay? It's not just like, okay, archaeology, is there a hole in the pyramids that I can go find gold or whatever?
There's a lot of people who are very curious about what's underneath the pyramids.
A lot of people care a lot about that. But I imagine that people living around volcanoes care a lot about whether there's a hole in their volcano, right, where the magma could come out. And so they've actually used these detectors on volcanoes, like Mount Vesuvius, Mount Etna, Stromboli. All three of those are in Italy. You also have Sakurajima, which is in Japan. And what they've done is using this muon tomography, they've mapped out the internal density of that volcano to see where the magma chambers are, where there's maybe less pressure. So if there's like an eruption, which way would it go? Because it would go to the path of least resistance through this like lower pressure part. So it reveals these like lava plugs, magma conduits. Again, though, there's a limitation. Because we are relying on cosmic rays, which the flux is so low, you're only going to get a static image. You need a year to take this photograph. You need a year to take this CAT scan. And then once you have the year, you have a static image of where the volcano is. But it would be really nice if we had so much flux, right, that I could get like a moving picture of what is happening inside the volcano using muon tomography.
So until this day, what we have is we've discovered a methodology by which to map large objects, look inside of large objects, such as the pyramids or volcanoes, but two of the primary limitations have been it takes a really long time to get a static, not motion image of these things because the frequency by which muons pass through them is so low. very low.
Exactly.
Right? Okay, so that's the foundation of where the story now picks up from.
Exactly. And now we pick up with this paper. Okay, this paper came out in the Physical Review Accelerators and Beams. It was a team at the Bella Center at Lawrence Berkeley National Lab. They used the laser plasma accelerator. Okay, and they did something very cool, which is they used a beam. They used an apparatus that's only about a meter big to create a very powerful muon beam. Okay, and in order to do that, they did a kind of physics that is very akin to wakeboarding. Have you ever gone wakeboarding?
So I've only gone once, and I immediately almost got a concussion the first time I got up because I just fell and slammed my face into the water.
Yeah, this is why I never go into water. So I have never gone wakeboarding, nor will I ever go wakeboarding. But wakeboarding is a very useful analogy for the physics that's going on here because it's quite incredible, right? Usually to make muons, you need a massive particle accelerator, and that massive particle accelerator then bombs into like something, and then that something, the interaction of all of the highly energetic particles with whatever target is going to create your muons. That's usually how you do it. Here, they've created an electron gun, effectively, that is extremely fast, very, very high energy electron guns with a short rifle in some sense. And what they're doing is wakeboarding the electrons. Okay, so here's what's going on. In wakeboarding, right? What you're doing is the boat goes at a really high speed, and then you got a surfer that surfs the waves of the wake that the boat makes, right? And you don't even need like a rope to tether you to the boat. There's like, I think there's like a photo of Mark Zuckerberg just like with an American flag, right? You know that one? Yeah. So like, you know, you don't need you can just, the waves themselves have enough structure and energy.
Right.
You can stand on top of those and then just go, right? Yes. And you can ride that energy.
Yes.
That's what they're doing. That's what they're making the electrons do that. So what they do is they've got an ultra short laser pulse, okay? And they're going to fire it into a gas. It's hydrogen doped with nitrogen. Okay, and what this...
I just want to say, hydrogen doped with a little nitrogen is such a funny sentence.
It's, I guess it's used a lot in like chemistry for like semiconductors. Doped meaning like you're removing some other stuff and you're putting some other stuff in.
Yep.
Yeah. And so what that's going to do is that laser is going to go in and it's going to create a plasma, because the laser is going to push out a bunch of the negative charges, and you're going to get free electrons, and you're going to get these positive nuclei. Now, all of a sudden, you have a bubble of positive charge, okay? And then if some straggly electrons get trapped in that bubble, they're going to ride that bubble, and because it's positively charged, they're going to want to get the hell out of there. And so you're going to push these electrons out.
Yes.
And they're going to be accelerated by these powerful electric fields. And you can get somewhere like several billion electron volts, like giga-electron-volts in a 30 centimeter plasma channel.
That's crazy.
Okay? And versus like, usually that takes hundreds of meters of traditional accelerators. Like SLAC does this, and SLAC requires like a massive thing that goes under the freeway. And, you know, so this is really cool that they're able to do this.
So
okay?
the part of the insight here is this miniaturization of being able to create these electron beam, these particle beams at like a very, very small scale, but still retaining
the energy
level.
Exactly. Yeah.
Which is obviously meaningful, because that means you can have smaller footprint of the accelerator.
That's the key. That's the key.
Idea.
And this is a relatively new technology, laser plasma accelerators. Okay. And they're still sort of coming into their being. They're still quite big. But the fact that, you know, we're getting to these high energies,
right,
and it's not like hundreds of meters, is a very promising step. Okay, so that's the first step. You got now an electron beam. Okay, a massive, really highly energetic electron beam. Now what you're going to do is you're going to dump that beam into a giant block of lead, steel, and concrete. Okay, and what that's going to do is the electrons are then going to interact with these heavy nuclei. Lead is a very heavy nucleus, right? And as it interacts, the electrons are going to slow down, and they're going to slow down, creating radiation. Because remember, we've talked about this a lot. If a charged particle accelerates or deaccelerates, it's going to release energy.
Yes.
Right? The only time somehow that it doesn't do this is in the confines of an atom, right? Because that's when
stuff gets weird.
Yeah, all the rules are off. But if it's a free electron and it's moving, and it starts accelerating or deaccelerating or changing direction, it's going to create this thing called Bremsstrahlung. It's a German word for breaking radiation. Okay? So all of that energy of the electron is going into high energy photons. These are gamma rays. And now those high energy photons will interact with the atomic nuclei to create pairs of particles. Pair production is something that happens when you got a bunch of energy in one spot, and that energy spontaneously splits into two particles, one that is the matter part, one that is the antimatter part. You get the matter-antimatter pair. And if the physics is right, then you're going to get a bunch of matter-antimatter pairs that are exactly muons and antimuons. Okay? If you tune the energy such that the energy is exactly E divided by C squared, the mass, remember E equals mc squared, right? So if the energy is exactly equal to the mass of two muons, one muon and one antimuon, then the energy is going to dump into muons and antimuons. That field is going to take over, and you're going to get a muon and an antimuon. And so what this ends up being is you get a collimated meaning it's all in one direction. That's where that word from the headline came from.
Yes.
All in one direction. It's directional, and it's a muon beam.
Yes.
Okay.
Yes.
So now we've got a muon beam. Very cool.
Right. From starting from this electron beam.
Yeah.
That now we put through this lead, steel, concrete substrate.
Yeah.
And it had this pair production that has now resulted in this, matter-antimatter muon pair.
Yes, exactly.
Okay.
Yeah. So now we got a muon beam all of a sudden.
Yes.
Right?
Yes.
You say it's a muon beam. How do you know it's a muon beam? Because everyone else is going to be like, how do you know it's a muon beam? How do you know it's not some other random particle? How do you know it's just not just another electron, right? So now you got to do the work of actually showing that it is a muon beam. So the detection system looks like this. This is the measurement room. We've got the laser coming in from the left. Then the laser creates this electron beam. The electron beam gets bombarded into this about 3 meters worth of lead, steel, and concrete. And on the other side is your detector. And that detector is what's going to catch the strays, catch these muon strays that are coming in. Okay? How do we make sure that the particles that are coming out are muons?
Yes.
Okay. I thought this was really cool because this is like a very simple test. Okay. Here's what they did. They said, okay, well, we know from all of the years of work on muons.
Because we've been doing this since the 60s.
Yeah. We know about muons for a while, right? Yeah. And we know that their decay, their half-life is 2.2 microseconds, right? So if we can characterize the half-life of these particles that are coming out and it's exactly 2.2 microseconds, then we're good to go. And that's exactly what they did. They collected data from 760 laser shots over 2 hours. So that's about 5 per minute. And then what they did was they triggered on the giant amount of electrons that would come out. And then they would look for a second signal, which is from when the muon would decay. Okay, because the electrons are coming out first, and then the muon would decay, and it would fit this exact exponential. They did a histogram. They fit an exponential to that histogram, and the exponential decay curve had a time constant that was exactly 2.24 microseconds, right? So it's like a telltale sign.
Yeah,
you can't ignore that, like, because this exponential decay thing, that's something that you learn about in undergrad physics, right?
Yep.
It's like at the end of the day, like it just took like a nice undergrad graph. Yes. To be like, yeah, that's a muon.
And so what's so interesting is it's not, with a lot of these stories, you not only have to create the new thing, right? In this case, how can we do muon generation at a smaller scale than like several building size accelerator?
Yeah.
But then everyone's going to say, well, how do you know you generated muons?
Yeah.
And so you also need to have a detection system on the tail end to validate your generator.
And not just detection, but like, how do you analyze that data to make sure that like you can convince everybody out there who's trying to say you didn't do it, right? Because there's so many people that are trying to do this, right? And everyone wants to get there first, so you got to really check your work. So that was really cool, right? So now they finally found they finally made this muon source, right? And now this gets over that cosmic ray limitation because now instead of a drizzle,
right.
If I could now make this such that I can point it somewhere, I don't have this drizzle of cosmic rays. Now I can just have a fire hose that's like aimed at whatever thing I wanna look at.
Yes.
Right.
Yes.
And the natural muon flux is something like, as I was saying, it's like one particle per square centimeter per minute, right? That's one particle through my fingernail per minute. This thing is going to be 40 times as much, okay? And this is the LPA source. That's what it looks like. It's just kind of a tabletop looking experiment. I mean, obviously there's a bunch of stuff in the building that is supporting this tabletop experiment. So it's not It's not so trivial to put this in the back of a truck or something like that. But at the end of the day, it's from this laser plasma source.
Yes.
And even at 1 hertz, it's going to be 40 times the particle delivery rate of cosmic rays, right? And it's an order of magnitude reduction in exposure time. Now you can start doing the same kind of muon tomography of your pyramid or whatever, but instead of taking like years, it's going to take maybe a few days. Right?
Which is like, if for anyone who's trying to do any of these aspects of archaeology, geology, these things where you want to look at these massive structures, that time efficiency is, I mean, incredibly meaningful. It reminds me very much of like the time efficiency of having like the Vera Rubin Sky Observatory.
Exactly.
It's the same kind of thing where it's like you're having more frequent, high quality data that's just becoming available because of this fundamental understanding.
Yeah. And it's only the beginning, right? Because like these lasers now, they're going to get much, much better. Right now, these guys are doing like the top this thing can shoot the electron beam at is about 1 hertz, right? But we could be getting to kilohertz, which is thousands of shots a second, right? And then that's another 3 orders of magnitude above what we already have. And so now you can start doing, okay, instead of a few days, now you got a few minutes. Right. We can, and then now that becomes really crucial. Suppose we think a volcanic eruption is happening.
Exactly.
We can go there and we can monitor the volcano every minute and look at the internal dynamics, right?
Yes.
And be like, okay, we need to evacuate now, or maybe we got a few more weeks.
That's actually a really practical, real world use case for this, basically as close to real time detection system that you can imagine. Extrapolating this, if you increase that source from 1 hertz up, and then you can also miniaturize the rest of the supporting infrastructure to some sufficiently small thing, which can be, it could be multiple 18-wheeler trucks. Like that's still crazy.
Yeah, man,
right?
It could be like multiple 18-wheeler trucks that you then like you put it somewhere and then you assemble together.
Right.
Like that's still crazy.
That's
that
still
was
crazy.
not possible. You couldn't do that with a massive detector. Now you could possibly do that in the next few years if things progress the way that they are, right? There's a lot of cool applications that I was reading about.
Yes.
That weren't completely obvious to me.
Okay.
But once I read them, it was like, oh, that's cool.
Okay.
Yeah, that's cool. So one of them is obviously like archaeology reimagined, right? You can now do targeted excavation.
Yes.
You can like point your muon beam at specific spots, and when you're excavating, you don't want to do like a brute force approach and just excavate everything. You've got limited time. You don't want to disturb the excavation in some sense. So you can like target and try to get to whatever cavity that you're trying to go to. You can also start imaging smaller objects like sarcophagi or like statues, things like that. You just stick that right in front of your muon detector. Real-time volcanology is something that we talked about. You can do near real-time observation of density changes like magma movement, gas pressure, lava plugs.
For the Yellowstone super volcano that always comes up, I mean, it'll be huge for that. Because we would be able to know.
Yeah, we'd be able to know, and that'd be really nice.
That'd be really nice.
That'd be really nice to know. There's also national security.
Okay.
And infrastructure, something I thought you would like.
Yeah.
So the speed of this muon tomography would be such that now we can scan cargo at the ports without opening the box, right? Because you can't do that with X-rays. The metal is too thick, right? But you could just stick a muon thing, and then so routine inspection of these shipping containers can happen in minutes now. You don't,
Yeah.
So then you don't have to trust the shipping manifest. You can literally be like, okay, is there something there? If there's any nuclear smuggling that's going on, nuclear waste and nuclear like rods and things like that are very dense.
Right.
They're going to interact with muons in very weird ways because that's just nuclear physics, right? So now all of a sudden you can have like safeguards and waste management, things like that. The other thing that was cool was civil engineering, right? Because like our infrastructure, let's face it, is quite old and needs repair.
Yes.
And you could take these muon beams to bridges and dams and buildings, and they could reveal hidden cracks, water infiltration, catastrophic failure. So it's a whole new mode of, it's like we've unlocked a new type of light,
right,
in some sense, right? We've unlocked a new type of imaging,
right. No, exactly. We what's so interesting about this? I mean, the NatSec implications got my gear stirring. I mean, it becomes very difficult to basically smuggle a dirty bomb anywhere.
Mm-hmm. Yeah.
Particularly, you can put these on any number of source platforms.
Yeah.
But the civil engineering one, I think, is so, particularly for where, this is true globally, but especially in the US, where we have now legacy infrastructure that is beginning to, I mean, the 405 has been shut down to one lane multiple weeks in a row.
Yeah, that's been the bane of my existence, dude.
And like deciding how, like what civil engineering projects are most pressing by having an actual data set that is not necessarily just time or, citizen complaints, but has like a data set. And again, this might be
we can like we can X-ray concrete,
right?
Yeah. Like that's what it is. We can now X-ray concrete and stone.
I can imagine. I mean, imagine putting this on this is getting a little ahead of the skis here, but you could have some sort of drone platform that you can then have and then do surveys local, just in terms of being able to distribute this to like lower cost use cases. I mean, muography in that context would have huge impacts.
Yeah. The only problem I'm thinking with the drone stuff is like because you need a detector.
Yeah.
Like with drones, it's really nice with radar because light bounces back. Muons don't bounce back.
You need the thing on the other side.
Yeah, exactly.
To be able to
that's
to
like even in X-rays, right? Like they always they put like a thingy.
Yep.
When they do the X-ray.
No, that's fair.
Yeah.
That's a very important distinction. Does not negate any of the actual benefits that we just talked about.
No,
which are meaningful. And so I guess the key advancements here that are sort of that are the next steps are higher energy beams, miniaturization.
Yeah.
Those are the two key areas for improvement.
Yeah. Those are the two key areas, and like the fact that this part has been solved, which is like making muons with a high energy electron beam, that part's been solved. Now the problem is miniaturization of it and making it higher power, right? Like making the hertz faster, the repetitive nature of that laser faster. Right now the laser like shoots and then it's got to recharge and then shoot again, right? But if you can make it rapid fire,
if you make it semi-automatic,
then exactly,
it becomes very interesting. It's fascinating.
Very cool.
I don't want to.
That was a cool one.
That's a really cool one. I don't want to muon from that story too soon.